This video will be the final video for Chapter 9 on optimization, where it looks at section 9.5 on the Maclaurin and Taylor series. The Maclaurin series is the expansion of a function around x equal to 0, and the Taylor series is the expansion of a function around x equal to some value of x, not necessarily x equal to 0, but x equal to x naught. Why do we need this? This can help with easy estimation of functions' values. And what does this expansion mean? The expansion means you transform the function into a polynomial function where the coefficients of the terms are expressed as derivatives. So let's say we have the function f of x equal to a0 plus a1x plus a2x squared plus a3x and so forth. If we take the first order derivative of this function, it will be a0 falls away, a1 plus 2a2x plus 3a3x squared plus n x to the power n minus 1. If we continue to the second order derivative, this will be equal to 2a2 plus 3 times 2x from this value times a3, and our nth value will be n times n minus 1 an x n minus 1 minus 1 x minus 2. Our third order derivative would be equal to, this falls away, 3 times 2 times 1 a3 plus, if we go to our nth order, it's n times n minus 1 times n minus 2 an x n minus 3. Our nth order derivative for this function is n minus 1 n minus 2 3 to 1 times an. So these derivatives will then form the base of our expansion into the Maclaurin and Taylor series. So the Maclaurin series before I continue with the Maclaurin series, an explanation. An exclamation mark like this in mathematics means faculty. So 2 faculty means 2 times 1. 3 faculty means 3 times 2 times 1. So if we go back to our derivatives, n faculty will be equal to this function. So this will be n times n minus 1 times n minus 2 times n minus 3 up to 3 to 1. Okay. So the Maclaurin series, let's do an example. If we have the function f of x equal to 1 plus x to the power of mu. So note this isn't a u, but mu, the Greek letter. So what we first need to do is we need to calculate the derivatives. So in this case, f prime of x is equal to mu times 1, remember the chain rule, times 1 plus x mu minus 1. F double prime of x is equal to mu times mu minus 1 times 1 plus x to the power of mu minus 2. Remember the chain rule, times 1. Our third order derivative is mu times mu minus 1 times mu minus 2 times 1 plus x times to the power of mu minus 3 times 1. Remember the chain rule. So our nth order derivative for this function will be mu minus 1, mu minus 2, mu, this will continue, let me just indicate, up to mu minus n plus 1, so the value is 4n of 1 plus x mu minus n. Let me just write that a bit more clearly. So up to mu minus n plus 1, 1 plus x to the power of mu minus n. Our second step for the Maclaurin series is we calculate the derivatives at x equal to 0. So f of 0 is equal to 1 plus 0 to the power of mu. 1 to the power of anything is 1. F prime at 0 is equal to mu. F double prime at 0 is equal to mu times mu minus 1. F 3 at 0 is equal to mu times mu minus 1 times mu minus 2. And Fn of 0 is equal to our function mu minus 1, mu minus 2 up to mu minus n plus 1. And then we write our series. So we have our function 1 plus x to the power of mu is equal to f at 0 divided by 0 faculty plus f prime at 0 over 1 faculty times x plus f double prime at 0 over 2 faculty x squared up to f n at 0 over n faculty times x n. So that is f of 0 is equal to 1, 0 faculty is 1, plus f prime at 0 is mu, 1 faculty is 1 times x, plus f double prime 0 is mu times mu minus 1 over 2 faculty, and then the last one, I'm just going to shorten this, over n faculty xn. And that is our Maclaurin series. For our Taylor series, we've said that this is not necessarily around x equal to 0. So in the textbook it explains the Taylor series, but I found a different way of writing the Taylor series. So the Taylor series, your function f of x is equal to the sum of n equal to 0 up to infinity of your nth derivative at x0. So remember the Taylor series, we look around our x0 over n faculty times x minus x0 to the power of n. So if n is equal to 0, what does this function become? It's f0 at x0 over 0 faculty times x minus x0 to the power of 0. So remember, this simplifies to f of x0 over 1 times anything to the power 0 is 1. If n is equal to 1, we have f prime x0 over n faculty times x minus x0, 1. If n is equal to 2, we have f2 of x0 over 2 faculty x minus x0 squared, and so on. So let's do an example. Say we have the function f of x equal to x cubed minus 10x squared plus 6, and we want to expand around x equal to 3. So we follow the same steps as for the Maclaurin series. So 1, find the derivatives. Now the question, up to which point do you want to find the derivatives? That is until the derivative is equal to 0. So f prime of x is equal to 3x squared minus 10x squared minus 10x, and 6 falls away. No, wait. Sorry, I'm looking wrong. So we have our function f of x equal to x cubed minus 10x squared plus 6. So our first order derivative is 3x squared minus 20x. Our second order derivative is 6x minus 20, and our third order derivatives is equal to 6. Our fourth order derivative is equal to 0. So we can stop at f3. So second, we find the values of the derivatives at x equal to x0. In our case, x equal to 3. So f of 3 is minus 57. F prime of 3 is equal to minus 33. Second derivative at free is equal to minus 2. And the third derivative at free is equal to 6. And now for our Taylor series. So our Taylor series, f of x is equal to f0 or f. So remember, it's f at x0. So it's f0 at 3 over 0 squared times 1 plus f prime at 3 over 1 faculty times x minus 3 plus f double prime at 3 over 2 faculty times x minus 3 squared plus our third derivative over 3 faculty times x minus 3 cubed. So we've calculated this value minus 57. Remember, 0 faculty is 1, so times 1. Plus, we've calculated this value as minus 33 over 1 faculty is 1, x minus 3. Minus plus 2. The second order derivative at 3 is minus 2. 2 faculty is 2 times 1, x minus 3 squared. Plus the third order derivative at 3 is 6. 3 faculty is 3 times 2 times 1 times x minus 3 cubed. And then we can just write it slightly neater. And that is our Taylor series.